This is multivariable calculus, and in this video I'm going to talk about section 15.5, applications of double integrals. So we just finished with sort of our first unit on multiple integrals, and we talked a lot about double integrals and how to set them up and how to solve them. But really, it's important to understand why you would even need to know something like that. And that's what we're going to focus on for these next several sections and sort of, what I call this next unit. We're going to start talking about applications of double integrals. For this one, we're primarily going to focus on mass and center of mass and moment of inertia. But there's other things we can do with these two, which you'll see. And then we're eventually going to look at these same ideas and start using triple integrals. So what we're going to look at first here is the idea of density and mass of what we call a lamina. So when we are talking about a lamina, we're talking about a 2D object. And you can see here, basically what we're saying is we've got some 2D object where it's a very, very thin object. And so the thickness of it in terms of its mass is going to be negligible. So eventually we'll get into three-dimensional objects, and that's where we'll get into triple integrals with these same ideas. So when we are trying to look at the mass of a lamina, we have to know its density. And sometimes we're going to have a density that is constant throughout, and sometimes we're going to have a variable density. When we have a constant density, then essentially what we have to do to get our mass is we have to multiply our density times the area that we have, and that's going to give us our total mass. Now, there's a couple of things here that I want to point out. Sometimes these notations get a little bit confusing because we interchange variables now that we're talking about physics applications. This variable rho here, when we're talking about density and mass, that rho is actually representing the density. So keep that in mind. We've talked about that rho in the context of spherical coordinates before, and it had a different meaning. So when we're talking about density and mass, that is going to represent the density. Okay, so the main idea here is if I have a constant density, then all I have to do is essentially break this thing apart. You can see over here we've got this kind of irregularly shaped lamina. And if I want to find the total mass that I have, all I have to do is break that into a bunch of subregions and then multiply the area times the mass and then add those all together, and that's going to give me the total mass of that lamina. Okay, so it's not that difficult to do. Now, here's an example. It says a triangular lamina with vertices 0, 0, 0, 1, and 1, 0 has density rho is equal to 3. Find its total mass. Well, there's a couple of ways to go about this. I'm going to show you the easy way first because we've essentially just got a triangle here. If I wanted to find my mass, remember it's just the density times the area. Well, let's think about what this would look like, right? From this perspective. We're looking at the point 0, 0, we're looking at the point 1, 0, and we're looking at the point 0, 1. So essentially, I've got this triangular region where, we've got an area of 1/2. So if I want the mass, it's just the density times the area, and I'm going to get 3/2. Okay, so now let's look at this in more of kind of a general sense, because most of the time we're not going to have these simple geometric shapes. So to do that, it's still the same general setup, except now I'm going to use a double integral because I'm going to assume that I've got a region that doesn't have this, simple geometric shape where I can just use a formula. And what I'm going to do here is I'm still going to use my density times my area, but now my area is going to be broken into small incremental pieces. And I'm going to choose to integrate with respect to y first this time, primarily because this is the line y is equal to negative x plus 1. So I'm going to choose to integrate with respect to y first, and you can see y would go from 0 to negative x plus 1, which means that my x then goes from 0 to 1. And if we were to solve that out, you would end up with the exact same thing. Mass is equal to 3/2. Okay, so just keep that in mind. Most of the time we're not going to have these really, really easy setups like that where it's a triangle. We're going to have irregular shapes like we were looking at with our double integrals for the last week or so, week and a half, and that's how we're going to be calculating mass. Okay, so this is just looking at now when we have what's called a variable density. So most of the time when we have an object, we're going to be dealing with situations in our applications where the density can vary. And depending on where you're located on that object, it's going to have a different density. And so when we do that, now we have to account for the fact that our density is varying, but where that comes into play is that instead of having a density like we had on the last problem where density was 3, now we're going to have a density that is a function. And it'll be a function of x and y when we're dealing in 2 dimensions. Okay, so the idea is generally the same, right? If we want to find the total mass, we're going to look at all of our subregions. We're going to add all of those small pieces of mass together, and that's going to give us the total mass. So it's the same general setup. It's just a little more complicated from the standpoint of actually solving the integral out, because now I don't have just a constant times dx dy or a constant times dy dx. Now I'm going to have to actually do a little bit more work when I solve these double integrals out. Okay, so let's take a look at the exact same triangular lamina we were just looking at, but now we've got a variable density. So we have density equal xy, find its total mass. Okay, so when we do this, what we want to think about, is kind of the same thing we were looking at before. I could do this and think about, okay, I know what the area of the lamina is, but that doesn't help me this time like it did last time because I've got a varying density. I have to break this into smaller pieces. So when I'm looking for my mass, I know I'm going to take a double integral over my region, and my density is xy, and then I'm going to have to break my area into those subregions. And again, I can do this in terms of x first, in terms of y first. It doesn't really matter. But for the rest of this is going to look a lot like the one that we just did. Remember, we talked about those limits of integration going from 0 to negative x plus 1 for the y, and 0 to 1 for the x. So it's the same setup, except for now when I'm solving this integral out, it's going to be a little bit more work because I've got to actually solve the integral. I can't do any shortcuts for this one. So it turns out when you solve this out, you get 1 over 24 as your mass. Now, sometimes you're going to have units. Most of the time you're not, because we're kind of looking at these in a general sense. But if you have units, you want to give units on your solution. Okay, so the main idea behind all of this is that, we're trying to get into some kind of physics applications, and knowing how to find the mass of an object is sort of where we start from. So this is typically going to be a piece of what we need to do, and then we're going to build onto that because we're going to be looking a lot for center of mass, and we're going to be looking for things like moment of inertia. So that's all going to be mass-based. Okay, so let's take a look at how we actually find, if you want to call it the center of gravity or center of mass, those are interchangeable terms. But what that means is if I had some object and I were to place, and this we're talking about a 2D object here, if I were to place that object so that the center of mass were sitting on a point, then that object would balance on that point. So it would balance horizontally. So what we're looking for here then is, this point from an x perspective and a y perspective, and you'll see this notation used. So you can see the x with the bar over the top and the y over the bar with the bar over the top. That's indicating that we're looking at the center of mass. So to find this, we've got to take into account kind of what's going on with this from the perspective of what's making this thing want to rotate or not want to rotate. Okay, so when we look at this, we have to concern ourselves with what we call a moment. And the moment is the tendency of the mass to produce a rotation about a point. So if we're at some point on our object and we're not at the center of mass, it's going to want to rotate either in the x direction or the y direction or both. And that's what the moment is a calculation of, is, how much does it want to actually rotate? So the way that we find that, the moment is dependent on how far you are from the axis you're looking at rotation around. So for example, if I'm going to rotate about the x-axis, I'm going to be thinking about how far is my mass from the x-axis. So the further I am from the x-axis, the more it's going to have a tendency to want to rotate about the x-axis, or the further my mass is from the y-axis, the more it's going to want to rotate around the y-axis. So you can think about when it's balanced perfectly and I'm at the center of mass, that means my moments around the x-axis are all balancing out. What I have above the x-axis and what I have below the x-axis, those are essentially canceling each other out. Same thing around the y-axis. What I have on the right side of the y-axis and the left side of the y-axis, those things are kind of canceling each other out, and that's making this thing balance in both directions. Okay, so first thing we do then is we calculate the moment, and then to find the center of mass, we can just divide by our mass. So if you look at what's happening here, when we look at our moment, we are essentially, for the x moment, we're multiplying by y to our mass. And the reason we're doing that is because, again, we're thinking about rotation around the x-axis. We're going to want to rotate around the x-axis as we have more mass, either above or below the x-axis. So that's why the y is taken into account there. And then the same thing with the moment in the y direction. We're looking at how far have we moved in the x direction with that, or how far away from the axis in the x direction are we? Okay, so then when we have calculated those moments, if we want the center of mass, then all we have to do is take the moment that we have and divide by our mass, and that's essentially sort of giving you that point where everything's going to average out. So we're going to essentially find the moment and then divide by the mass, and it's sort of like, you can almost think of it like an average function value, right? So when I think of it that way, you can see for this first setup, when I'm looking for my x center of mass, I've got my moment, and then I'm dividing by the mass here. Very similar to what we see when we look at average function value, right? Where we would do an integral and then divide by our area or divide by our volume, whatever it is when we're looking for average function value. Okay, so we then are going to be able to find this point on this lamina. So you can see now that point x bar, y bar is going to be the point where it would be perfectly balanced. Okay, so obviously when you have, a constant density and you have something like, let's say, a disk, the center point, the center of mass would be the point where it would perfectly balance. But most of the time, we're not going to deal with simple objects like that. We're going to deal with objects that are irregularly shaped, and we're going to deal with objects that have varying density. Okay, so let's take a look at an example of this. It says, find the mass and the center of mass of a triangular lamina with vertices 0, 0, 1, 0, and 0, 2 if the density function is rho is 1 plus 3x plus y. Okay, so let's first talk about what this region looks like. So I would recommend you always do a little sketch of your region just so you kind of know what you're dealing with. So we know we're dealing with the point 1, 0, the point 0, 2. So I'm just going to label that as 2 and 1, and the origin. And so this is my region right there. Okay, so if I were to look at the equation of this line, that line is y is equal to 2 minus 2x. All right, so now I've got a good way that I can use to set this up, right? This is similar to what we did before with the mass, except for now I've got a slightly different triangle, but same general idea. Okay, so first thing I need, if I'm going to find my center of mass, is I need to find the mass. So I know the mass is going to be the integral, double integral over this region. I'll just call the region R, and the density this time is 1 plus 3x plus y. And then I'm going to have, again, dA. So again, I can choose to integrate with respect to x or respect to y first. It doesn't really make a difference. Since I have y in terms of x, it's easier for me algebraically just to go ahead and go with the expression I already have. So I know in the x direction, I'm going to go from 0 to 1. In the y direction, I'm going to go from 0 to 2 minus 2x. And then I'm just going to integrate this 1 plus 3x plus y. And I've got dy dx. And again, I just chose to integrate with respect to y first. It doesn't really matter which way you do it. Now, when we get to these points, to the point on the problem here where we've got these set up, I'm not going to go through solving these integrals out anymore. I'm going to assume that you guys know how to solve these at this point. So we're just going to go through the setups, and then I'm going to jump to the solution. So it turns out our mass here is 8/3. Okay, so now let's take a look at finding the actual center of mass. So let's talk about the formulas for these a little bit. And X bar is the one I'm going to start with. And so the way we set this up is we use the moment about the y-axis divided by the mass. And the reason we do that when we're looking for the X center of mass is because the moment about the y-axis is what involves the X coordinate, right? So the distance I am in the X direction on either side is going to give me a different moment depending on the mass that I have at that point. So this is essentially the moment in the Y direction is the one that involves the X coordinate. So in the end here, I'm going to have 1/8 because I've already calculated my mass. And then for the moment in the Y direction, or the moment about the Y axis, I should say, I'm going to have the double integral over that same region. And it's going to be X times 1 plus 3x plus y dA, right? Okay, so that's my setup. Now, we actually need to solve this out, but we know what the limits of integration are going to be. We know how this process works. So this would essentially be the same as 1/8, or I'll just say 3/8. 3/8 times this. We know we're going to go from 0 to 1 in the x direction. We're going to go from 0 to 2 minus 2x in the y direction. And then when I distribute that x through there, I'm going to get x plus 3x squared plus xy. And again, I'm integrating with respect to y first, and then x. Okay, so if you solve that out, it turns out that that double integral is actually exactly equal to 1. And so what I'm going to end up with here for the x center is going to be 3/8. Okay, so now we can do the same thing to find the y center of mass. So if I want this y center, I'm just going to do the moment about the about the x-axis divided by the mass. And so that's going to end up, and I'm not going to go through the general setup here first. I'm just going to jump straight to the double integral with my limits of integration. So I'm going to have 3/8 times the integral from 0 to 1 and 0 to 2 minus 2x. Now remember, this time we would be doing y times 1 plus 3x plus y. So that's going to give me y plus 3xy plus y squared. And again, dy dx. Oops. And when I solve that whole thing out, I'm going to get 11/16. So now I've got my center of mass of this object. It would be at the point when x is at 3/8 and y is 11/16. So that's how I would give my center of mass, is just 3/8, 11/16. So remember, that's just a coordinate on my graph. If I go back and look at the actual object that I had here, oops. But if I look at this object that I had here, remember, essentially, if I were to go to 3/8, 11/16, I'm going to be at a point, I'll just estimate it here, somewhere around here. That's where we're saying our center of mass is. So it kind of makes sense. Even though we have the varying density, you can kind of picture where that would be and see if that is reasonable. Now, sometimes you'll make a mistake somewhere and you'll start getting coordinates that aren't even within your object. It's obvious you've made a mistake in a situation like that. So use what you know about the problem to help you catch little errors like that. All right, so the last application we're going to talk about today is called the moment of inertia. And the moment of inertia is really, it has to do with how much of our mass is further away from our axis of rotation. So the more mass we have further away from the axis of rotation, the more that object is going to tend to want to rotate, and it's going to take either more or less torque to speed up or slow down that object if it's rotating around the X or the Y axis. So when we are looking at moment of inertia, it has to do with the distance squared away from the axis of rotation. So it's a little bit different than what we were looking at before when we were talking about the moment. Now we're talking about moment of inertia, which has to do with more of like an acceleration type of setup. So you can see we have this mr squared as our setup. Now, from the standpoint of how do we find the moment of inertia? Well, if we're going around the x-axis, just like we were thinking before with finding the moment of inertia is going to be essentially measured in the same direction, right? If I'm going to look for a moment of inertia around the x-axis, I'm going to be thinking about how far am I away from that x-axis in the y direction. So take a look at the setup here. Looks very much like what we had for the moment, except with moment of inertia, instead of a y, I have a y squared here. Okay, so then our double integral is going to add up all of those little pieces, and when we get all of those pieces, that's going to tell me essentially the tendency of that object to rotate about the x-axis. Then we can do the same thing for the moment of inertia about the y-axis, and again, same idea here. And sort of what you're thinking is, if you had the majority of the bulk of your mass far away from your axis of rotation, your moment of inertia is going to be very high. If the bulk of your mass is close to your axis of rotation, your moment of inertia is going to be very low. So if you think about, when you're thinking about rotation of an object, you know, when you are very far away from its center, so let's say we had like a rod that had a constant density all the way through. If I went to the center of that rod and I pushed on the end of the rod, it's going to want to rotate, right? But if I had that same rod where the bulk of the mass is at the ends of the rod, if I push on the end, it's going to want to rotate a lot more because there's so much mass at the end as opposed to the center. If I had an object where the bulk of the mass is in the middle, and again, I push on the outside, it's not really going to want to move very much. I can push it, but it's going to stop very quickly because all of that mass is in the center. So I'll talk about in class some ways that you can kind of practice with some things at home to get your head wrapped around this. But for now, we'll just think of it from a formula standpoint. Okay, so let's talk about then moment of inertia about the origin. When we look at moment of inertia about the origin, now we're going to take the x and the y moment of inertia into account. And you can see the moment of inertia about the origin is now x squared plus y squared times rho xy. Well, if you think about how that's set up, the x squared is multiplied to the rho, the y squared is multiplied to the rho. It actually turns out that our moment of inertia about the origin is just the same thing as the x moment of inertia plus the y moment of inertia. Okay, so anyway, we'll typically just look for the x and the y, but sometimes we're going to want to look for the moment of inertia about the origin as well. All right, let's take a look at an example. So it says, consider the rectangular lamina that occupies the region described by these inequalities. So x, we're going from 0 to a, y, we're going from 0 to b. Assuming the lamina has constant density, show that this is true. Now, we got a constant density this time, right? So it's very, very easy for us to calculate the mass. So the mass part of this is sort of done, right? And if you look at the setup, when we do the moment of inertia, we do have the mass kind of factored into this. We don't do a separate mass calculation, but it's sort of embedded within the setup that we're going to use. Okay, so to do this then, all we have to do is that simple setup. So if I want the moment of inertia about the x-axis, all I have to do is decide which way am I going to integrate first. I'm going to choose to integrate with respect to y first. Since this is a rectangle, it really doesn't make a difference. But the reason I'm going to do y is because I know that when I integrate, there's going to be a y squared in my setup here. So remember, it's going to be rho times y squared. And then I'm going to do dy dx. Okay, so again, I could have done dx dy. It's going to give me the same result. In the end, though, you'll see that your moment of inertia about the x-axis is rho AB cubed over 3. And then we can do the same thing, moment of inertia about the y-axis. Same limits of integration, 0 to a, 0 to b. This time I'm going to have rho x squared dy dx. Okay, so the calculations themselves are fairly easy to do because you just have these kind of standard setups to use. So what you might struggle with if you don't have a lot of physics background and a lot of practice with physics applications, you might struggle a little bit with what does this actually mean? And that's what we'll spend some time talking about in class. All right, so last one here. It says find the moments of inertia. So we want the moment about the x-axis, the y-axis, and the origin. For the lamina, for the region D that's bounded by y equals 1 minus x squared, y equals 0, and rho is ky this time. Okay, so first of all, let's take a look at what are we describing here. So we're looking at 1 minus x squared. Okay, so 1 minus x squared means we've got a parabola that has a y-intercept at 0, 1, and it opens down. So it's going to look kind of something like that. And they're talking about also being bounded by y equals 0. So we're really looking at this region up in here, right? So that's the region that I'm looking at. And our density this time is k times y. Okay, so fairly easy to do here. If I want the moment about the x-axis, I'm going to choose to integrate with respect to y first, primarily because you can see we're bounded by a function in the y direction. So in the x direction, I know I'm going to go from -1 to 1. And then in the y direction, I'm going to go from 0 to 1 minus x squared. And then I've got my y squared, because that's the distance away from the x-axis squared, times my density, which was ky, and then integrate with respect to y, and then with respect to x. Okay, and when we solve this out, it's a little bit of work to get this solved out, but we get 64 over 315 k. So we have sort of a general solution here because we had that constant k within our density this time. Okay, so now we can do the same thing, moment about the y-axis. So if I want the moment about the y-axis, I know most of this setup's going to be the same limits of integration. The only difference this time is now I'm worried about how far am I away from the y-axis, and we're going to square that distance. So x squared ky dy dx. And when I solve that one out, I get 8 over 105 times k. Okay, so again, I'm skipping the double integral solutions here, so there is a little bit of work involved, but conceptually, the setup is fairly easy to do. Okay, so they actually also asked us for the moment about the origin this time. So the moment about the origin, remember, is just the moment about the x plus the moment about the y. And remember, it's not so much that it's the x plus the y, it's just that that's what it simplifies down into, because we're thinking about the distance from the origin in a two-dimensional plane. The distance from the origin is just the square root of x squared plus y squared, right? So that's kind of what we're thinking about from a distance perspective, is if I went x squared plus y squared, I'm essentially doing the distance squared. Okay, so in this case then I've got 64 over 315k plus 8 over 105k. And when I add those up, I'm going to end up with 88 over 315 times k. Okay, so that would be my moment about the origin. Now, like I said before, if you had a really high moment of inertia, a high value for the moment of inertia, that means that it's going to take a lot to speed up or slow down that object when it's rotating about that axis. If you had a very low number, that means it doesn't take very much to stop it from moving when it's rotating about that axis. Okay, so like I said, we're focusing on physics applications here, but there's a lot of different types of applications you can use these double integrals for. And we'll look at more. We'll talk about surface area, the next section that we go to, and there's some other things. There's a lot of things we can do that deal with statistics. There's other applications we can look at, but for this class, we're primarily going to focus on physics applications.